the D field is actually equal to c, the speed of light. So you can see that E is 3 times 10 to the 8th bigger than V. So I haven't called this to scale. The E field is very large. The corresponding D field is very small. We are going to consider, for the purposes of the diffraction grating, we're just going to be thinking about the E field. So here is my E field. That's the value of E. And the classic formula for a wave is E equals E naught times the sine of kx minus omega t. I'm not going to go through what that means because we don't really need it here. Safe to say that if you look at my video on waves, you'll see how we derive that. E naught is the maximum amplitude of the wave. But of course the wave is oscillating all the time. Now what happens if you get two waves coming from the same monochromatic source? This is the crucial reason why we have the same source. Through two slits. Then you will get a wave coming through one slit, and you will get a wave coming through another slit. And if the two are in phase, in other words, if we've got condition for brightness, then these two will combine to, as it were, the superposition to get you a double crest and a double trough. And we can represent that vectorially. We can say, well, this is really the E field. So here's the E field for the first wave. We'll call that P. And added to that is the E field for the second wave, which will also be E because they both come from the same source. So they're both going to be exactly the same amplitude. And how do you do vectorial addition? Well, in this case, it's trivial because they are both in phase, so there's no angle between them. And consequently, the total E field will be 2E. So you get twice the electric field when the two waves are in phase. That is constructive interference. So if you have a diffraction grating with capital N slits, then I think you will see that the total electric field, when you get constructive interference, will not be 2E, but NE. In other words, the size of the electric field, when all of those waves are in perfect alignment, will be N times the size of the individual electric field. But what happens if these two waves are out of phase by delta? There's the first, and here's the second. It doesn't start here, it starts here. So it is that distance, and that distance is delta out of phase. Now if we do vectorial addition, here is the E field for the first wave, but when we add it to the E field of the second wave, we must do so at an angle delta. Up here, the angle was 0, so it just becomes a straight line. But here, the vectorial addition of two E fields, they'll both be the same length. I better make it. They'll both be the same length E because they both come from the same source. But the vectorial addition, if you want to add vectors together, you always put the vectors tip to tail, and then you draw a line from the starting point of the first vector to the end point of the last vector, and that distance represents the value of the E field when the two are delta out of phase. So in other words, the total ET will equal E plus GE, plus you've got to recognise that you've now got an angle delta to take into account. Well, what happens if you've got my diffraction grating with 4 slits? And you've got the waves coming off such that each of them is an angle delta out of phase with the others. Well then, you'll have the first E field you can draw like this. The second E field is exactly the same length because it's the same source. Because don't forget we've got a single source shining into these 4 slits. will be at an angle delta. The third E field will be at an angle delta. And the fourth E field will be at an angle delta. And to find the total E field, you have to do the vectorial sum of 4 E's. If you've got n, capital N slits, then you're going to have n waves, all delta out of phase. So you've got to do the vectorial sum of capital N individual E fields. Before I do that generally, let's just look at the situation in some specific cases. Suppose delta equals pi over 2, or 90 degrees. So each wave is 90 degrees out of phase, or a quarter of a wavelength out of phase with the next one. Then your E diagram will look like this. There is your first wave, there's the second, which is 90 degrees out of phase. Here's the third, 90 degrees out of phase, and here's the fourth. I'm thinking of a 4-slit diffraction grating. What is the length of the E vector? Well, it's the distance between the start of the first E vector and the end of the last E vector, and that's 0. So when the waves are pi over 2 apart, or 90 degrees apart, the E vector total will be 0, and that's the condition for destructive interference. You get a dark fringe. What happens if delta is equal to pi, which equals 180 degrees? Suppose all the waves are half a wavelength out of phase. There's the first one, there's the second one, there's the third one, there's the fourth one. Each of them, each successive one is 180 degrees out of phase. What is the distance between the start of the first E vector and the end of the last E vector? Answer, 0. This will also produce destructive interference. Destructive interference, darkness. But what happens if delta is equal to 2 pi? Well, in those circumstances, you're in phase, because 2 pi is 360 degrees, it's one complete cycle. So if you've got 4 slits, you just add the 4 vectors up. Each of them is 2 pi separated from the other, which is the same as 0 when it comes to cycles. And so the total E field is equal to 4 times the individual E fields. Or if you've got n slits, capital N slits, the total E field will be NE. Now, it's worth noticing that the E field is not a measure of brightness. The brightness varies as n squared. So you don't get 4 times the brightness with 4 slits. You get 16 times the brightness that you would get from one individual slit. But I now want to address the question, where delta is not one of these specific points, how do you generally calculate the total E field where you've got any value of delta? So how are we going to do vectorial addition in order to find the resultant E field? The way we do it is we construct a circle. There's the circle, and this one is the centre of the circle, and obviously the circle will have radius r, so that's r, and I'm going to do this for a 4-slit diffraction grating. We'll generalise it in a moment. And what I'm going to do is to mark off this distance between these 2 points here. I'm going to mark off such that there are 4 equal points. And these are straight lines I'm drawing now. Don't look at it, but they are straight lines, 4 of them, and each of them will be my value of E, and each of them will be an angle delta separated from the previous one. So these are delta out of phase, each one moves off at an angle delta. So here, this is the extension of the first one, and the angle between the two is delta. If I draw radii to the beginning and end of each of the E fields, know geometrically that if each of these lines is an angle delta from the previous, then the internal angle here is also delta in each case. So the total angle is 4 delta. Or, if I had capital N lines in my diffraction grating, this total angle would be capital N delta. You could also say that the angle, the external angle here, will be pi, which is 180 degrees, minus N delta. I hope we're all agreed on that. And what we're trying to find is the length, the vectorial sum of these 4 G vectors, which is this one here. You join the start of the first E vector with the end of the final E vector, and you have to do vectorial sum addition to find out what the total E field is. I'm going to do one more piece of geometry. I'm going to drop a perpendicular down here to the first E field. The length of this distance here is obviously going to be E over 2. We know that the radius is R, and we know that this is a right angle. So we can say that E over 2 divided by R is the sine of that angle, and that angle will be delta over 2 because we have effectively bisected it with this perpendicular here. So what we're saying is that E over 2 divided by R is equal to the sine of the angle, which is half of delta, so sine of delta over 2. And now we make use of a bit of mathematical geometry, which says that if you have an isosceles triangle where these two sides are distance r, and this is GT, you know, notice that that's exactly what we've got here, R, and ET, and you have an external angle, which in our case is pi minus n delta. In those circumstances, GT is equal to twice the radius, so 2 times r, times the cosine of half this angle. So it's the cosine of pi minus n delta over 2. That's just a geometrical theorem. Provided you've got an isosceles triangle, the length of the third part of the triangle is equal to twice the isosceles part of the triangle, multiplied by the cosine of half that angle. So ET is equal to 2r times the cosine of half this angle. But we've just shown this relationship here, which means that we can write a value for r, and r is equal to half d divided by the sine of delta over 2. We got that from this formula here. R, take that up there, bring the sine delta over 2 down here, you get r is equal to e over 2 divided by the sine of delta over 2. So we've got this value for r, which we can substitute in here. And that gets us a rather difficult equation, that dt is equal to d times the cosine of pi minus n delta over 2 divided by the sine of delta over 2. Because the 2 and the half cancel out, so when you put r in here you get dt is equal to d times the cosine of pi minus n delta over 2 divided by the sine of delta over 2. I can simplify that a little bit further because the cosine of pi over 2 minus n delta over 2, I'll say that again, the cosine of pi over 2 minus n delta over 2 is equal to the sine of n delta over 2. dt is equal to E times the sine of n delta over 2 divided by the sine of delta over 2. Remember, pi over 2 is 180 degrees, so pi over 2 is 90 degrees, and the cosine of 90 degrees minus an angle is equal to the sine of that angle. So I've rewritten that formulae, and the question I want to ask is, what happens when delta goes to 0? Now, we already know what happens, because if delta is 0, all the waves will be in phase, and that is the condition for brightness. And so you will get a maximum where the total E field will be capital N, where N is the number of slits, times the value of the individual E field. But what happens if delta is 0 in this formula here? Well, if delta is 0, you get sine of 0 at the top, and you get sine of 0 at the bottom. So you get, and the sine of 0, of course, is 0. So you get 0 divided by 0. And that's indeterminate. But some clever mathematician has shown that if you take the sine of nx and divide it by the sine of x, then as x tends to 0, the value of sine nx divided by the sine of x will become n. Consequently, as the sine of n delta over 2 divided by the sine of delta over 2, as delta tends to 0, the value of the sine divided by sine term will be capital N, and consequently, when delta is 0, dt becomes d times the value of this term as delta tends to 0, which is n. And that's exactly what we had found before, that the total E field will be n times the value of the single E field. When delta is 0, all the waves are in phase. And just to remind you that the vectorial addition was trivial for a 4-slit grating. We just line them all up and we say that the total E field is 4 times the individual E field. And remember that at maximum, the intensity is proportional to the value of the E field squared, which means that's going to be proportional to n squared E squared. The square of the number of slits times the square of the actual E field itself. So if n is 4, the intensity is going to be 16 times the brightness of the individual field. Or more accurately, 16 times the brightness that you would get from a single slit. Now let's just consider the condition for brightness. Once again, I'm going to take just a 4-slit diffraction grating to keep it simple. We're looking at an angle theta, and if that is the condition for maximum, in other words, all those waves are going to be in phase, then we've already shown that n lambda is equal to d sine theta, where d is the distance between any two adjacent slits. That means that n lambda over d is equal to sine theta. And now we can plot a graph. And the graph is going to show intensity, or if you prefer, the E field, if you know which one you do, against the value of sine theta. We know that there will be a bright spot when sine theta equals 0. In other words, opposite the slit, there will be a bright spot. What this tells you is that there will be a bright spot for every value of every whole number value of lambda over d. So there will be a bright spot at lambda over d, and there will be another bright spot at 2 lambda over d, and so on. And there'll even be a bright spot at minus lambda over d, because the fringes are on either side of the central major fringe. Incidentally, I've drawn this as if the brightnesses will all be the same. They won't, but I'm just doing this for illustrative purposes.